Now, first let's discuss the transformers a bit, and then I have another interesting example for you. Now, what we call a transformer is mainly we have two solenoids. Okay, this is a ferromagnetic material. And then we just wrap two solenoids around it. And then another one over here. And here you just give some V1. And here you would measure, let's say V2, the potential across those 2 points. Now, the reason why we use ferromagnets is, if you remember when we were discussing ferromagnets, we said that they enhance the magnetic field significantly. If you put it in a solenoid, without the solenoid, without the ferromagnet in a solenoid, you will get some magnetic field. But if you put a ferromagnet inside the solenoid, then you will be enhancing your magnetic field by several orders of magnitude. So inside you have a huge magnetic field. Outside you will not have such a significant magnetic field. Well, if you just imagine the magnetic field is proportional to the intensity of the magnetic field lines, since inside we have a huge magnetic field, it just means that the ferromagnet kind of just traps the magnetic field lines. It doesn't let them disperse around. It just keeps them inside. So if you just send the current around this first solenoid, it will be creating some magnetic field lines. But since the magnetic field lines will be mainly trapped inside the ferromagnet, they will also go around the other solenoid. So this will be how the magnetic field lines look like. So all the magnetic field lines that go through the first solenoid, they will also go through the second solenoid. Now the flux through the first solenoid, let's say phi1, will be equal to, let's just say phi0 for the flux that goes through a single loop times N1. So this has N1 turns, and here we have N2 turns. So phi1 is nothing but N1 times phi0, and phi2 will be just N2 times phi0. Again, phi0 is the flux that goes through a single turn. So if we have N1 turns, the total flux that is through this solenoid is just N1 times phi0. Now, V1 is nothing but minus d phi1 by dt, and V2 is minus d phi2 by dt. So if you take V1 over N1, these are the relations that we have. Now if you combine these things, V1 over N1, this will be equal to V2 over N2. So you can change the potential by using the transformer. And how much it changes, it just depends on the number of turns that go through each one of the solenoids. Now, what is the point? Well, one thing is, if you remember, the power dissipated through a resistor is I squared times R. So, for example, if you want to carry some electric power through long distances, you would rather have a small current in your system. But if you want to have a small current in your system, what you do over here is, of course, you are increasing V, but you are not gaining energy. So if you are creating a current I1 over here, and another current I2 over here, I1 times V1 is also equal to I2 times V2. Because I times V is the power of your system, the power you cannot gain in power. So if you are increasing V, you are reducing the current that is running through it. So you just increase the potential so that there will be a small current running through your wire, and hence even if your wire has a very small resistance, even if your wire has a resistance, the power dissipated by that resistance will be very small. So you will be losing less energy as you are transmitting the electricity between different cities in a country. Now, of course, there is one thing that you should pay attention to. This relation holds only if there is a changing flux. The flux should be changing. That is, if you want to change the flux, you should be changing the current in your initial system. So for a direct current, you cannot use this. You cannot just take a transformer, connect one end to a DC circuit, a battery, and hope to get a larger power on the other side. So the potential should be created by this changing flux only. Under that circumstances, if you have an AC current, you get this change in the potential of your current. Any questions on this one? Then I have a question on, so let's say this is the top view of our transformer. Have you opened up a transformer? Yes. How many of you opened up a transformer, a charger? Did you open up a transformer? How many of you? Okay, 1, 2. Okay, just buy a cheap cell phone charger and open it up. You will see there is a transformer inside. And there will be one thing that you see. It is made, as your friend has pointed out, it's not a block of iron. It's just very thin sheets of iron connected together, not just a single block. Now the reason is this. So we have already studied, this is our solenoid. We had already studied what happens in a solenoid. If there is a time-dependent current running through it, you will be creating an electric field inside. And the electric field created inside the solenoid, it will be circular. Let's say it's in this direction. Just one sample electric field. Now, if this is a conductor, well, there's an electric field inside the conductor, so charges will start moving. But if the charges start moving, this iron block, it has a resistance. If there is a current building up, then we have also the resistance. It will be dissipating energy. You will be losing energy. It will be heating up. And that is not what you want. That's not something that you want. You would rather keep it at low temperature. So you should be preventing currents that go around such circles. This is what's called the eddy current. And in the video that some of you had watched, the thing was you have this aluminum block, and then you take this strong magnet. If you move the magnet strongly, fast in one direction, some of you had seen that this aluminum block moved with the magnet, although the magnet didn't touch the aluminum. The aluminum is not affected by the magnet. What happens is, as you are moving, you have a changing magnetic field, which creates an electric field in the aluminum, but that creates some currents in the aluminum. Those are called eddy currents. most of the time those are not things that you would like to have. For example, in a transformer, you wouldn't like to have eddy currents because that will cause the transformer to heat up. You will be losing power. You will be losing energy. So what you do is, rather than using this block of ferromagnet, you just divide it into very small sheets. You divide it into sheets, and in between these sheets you put some insulating material, an insulating glue. So since they are insulated, the current cannot really run around circles. They can only run within that very small sheet, and the component of the electric field within that sheet will be small. So you don't get large currents building up in your transformer, and you don't lose energy. Okay, open up a transformer to see what I mean. Any other questions? Not really. I mean, what you need to have is you just need to have a ferromagnetic material with at least two such things so that you will be able to wrap them around. That is what you would like to have. But you can use a block of metal, a block of ferromagnet, or you can just build these blocks by using these sheets. Usually they are built by using these very thin sheets. And the advantage, the reason why they use these sheets is that since you separate them by an insulator, you don't create eddy currents. Now let's continue with our previous example of the electric field created by the solenoid. Now we had the solenoid. Inside there is these magnetic field lines. They are uniform. And B, the magnitude was given by mu0 I n. Let's say this is the direction of I. And I is a function of time. This is what we said. What is the electric? We said that, okay, since the current is changing, there will be an electric field inside the solenoid. What about the electric field outside the solenoid? Will there be an electric field generated outside the solenoid or not? Remember when we were discussing the solenoid, outside is here B is equal to 0. Is there will there be an electric field outside? No electric field? No. Will there be an electric field or no? Your friends are saying that, okay, outside there's no magnetic field, so there's no flux, so there will be no electric field generated outside. That's the argument of your friends. Do you agree? Okay. Anybody else? It's neutral. Nothing is charged. And we connect it to a battery. The electric field will be inside the wire. So that will be changing the electric field. But what I'm interested in is what is the electric field outside of the solenoid created by this changing magnetic field? That's my question. Okay, let's see. There's no magnetic field, so there shouldn't be any electric field. So let's see if this is what we expect. Okay, so there's no magnetic field. The magnetic field is 0. 0 is just a constant. It doesn't change, so there's no electric field. So let's see if that is consistent. Okay, let's just imagine again this circle. Again, we have the same arguments. If there is an electric field, if there is one, it cannot be radially outward. It has to be invariant if we rotate our system around the central axis of the cylinder. So the only possibility is that the electric field should be circular. Now let's say the radius of the circle is r. E dot dl will be again just E dl. Again, we just say that this is a theta hat vector. The electric field dl we define as some positive number in the theta hat direction, and E is E in the theta hat direction. So this is 2 pi r E. Okay. This is exactly the same as in the previous example where we had assumed that this circle was inside the solenoid. Now, what is the flux? The flux, is it zero or not? Remember how we define this thing over here. We have this all of this area. We have the area. We divide our area into very small segments. And we just sum B dot ds, the contribution of B dot ds from each one of these small segments. Now this area is all of it. The magnetic field inside all of this area is not constant. It is zero in this ring. It is non-zero in this ring. So this flux going through this loop, through this area is non-zero. Let's say this radius of this solenoid is r, so the flux will be mu 0 I n pi large R squared. Positive or negative? It's negative. That's minus. Well, let's see, let's just put it in our law. 2 pi r times E, this should be equal to minus d phi b by dt, which is mu 0 n pi r squared di by dt. Or E is equal to mu 0 n over 2 di by dt r squared over small r. Which is non-zero. How come? Okay, we found it to be non-zero. If our theory is correct, if it is consistent, it should be non-zero, but how come? But you see, the magnetic field is zero outside, as your friends pointed out. We have a uniform, changing magnetic field only inside the solenoid. Flux is changing in time. That's how it's created. But we also said that physics should be local. It shouldn't depend on what's happening over there. Which electrons? You see, if it was for the electrons, the electric field line would start from the electrons and go to infinity or terminate at some positive charges. But this electric field doesn't start anywhere. The electric field is both inside and outside. We have non-zero electric field. We cannot. You see, if we would model it with a point charge somewhere, the electric field lines would just start from there. But you see, the electric field lines do not start anywhere. We will come to that, don't worry, but not yet. Let me remind you, re-ask you this question. What is this changing magnetic field? I mean, your friend was asking for the inside the solenoid. She was asking, where do we have these moving magnetic field lines? The same question holds over here. Do we have moving magnetic field lines outside? But you see, magnetic field lines, they have to close. They cannot be open. They have to close somewhere. If you are creating new magnetic field lines, they have to close somewhere. You see, if this is the picture of the solenoid, just a finite length solenoid, you can just assume it to be as long as you want. You can just take the limit, eventually take the limit that it is infinitely long. So these are the magnetic field lines. They do close. Now, if you are creating a new magnetic field line close to the current, they have to close. The magnetic field lines, they have to close. Now, what happens when we take the limit to be infinite magnetic field line is that, now, okay, before that, now the magnetic field, if you create a new one, it also has to close. If you push this magnetic field line towards the inside, the magnetic field line outside, it will be moving towards the infinity. Now, if you take the limit that the solenoid is infinitely long, what will happen is, once this magnetic field line is created, it will just move to infinity. But it will move. There is this moving magnetic field line even out of the solenoid. So although the magnetic field stays zero, that is the density of the magnetic field lines, it stays zero, there is no magnetic field line outside, the new magnetic field lines do go through our ring, creating this new electric field. This electric field, there is this electric field there. Okay, another example we will discuss. You see, you are saying that we should have magnetic field lines in this region, but their density is zero. But their density is zero. If I put, let's say, two of them over here, that would mean they have a non-zero density. Why? Well, the rate of change, well, you see, let's see. Now, from this picture, it's kind of trivial to see. Okay, yeah, there are a few things you can say. One is, first of all, we don't have infinitely many solenoids, so you can say that this is kind of a fringing effect. The magnetic field outside will be negligible. The magnetic field itself will be negligible, but its rate of change, its time rate of change will not be negligible. Something that is very small itself can be oscillating very fast. No, you see, the two things are different. One is the magnetic field, the other one is the rate of change of the magnetic field. The magnetic field can be negligible, but the rate of change of the magnetic field need not be negligible. Let me give you an example of a function who is negligibly small, but whose rate of change is infinitely high. Now, in mathematics, at least this is my argument, that the derivative will be large. So that will create a finite electric field. Physically, this is my argument. You cannot create just a linear magnetic field line. You have to close it down. And the magnetic field line starts from the currents. But since the magnetic field line outside is zero, it just means that this new magnetic field line that you create, it just goes to infinity almost instantaneously. This is creating the electric field. But you see, what we said was the electric field is created by these moving magnetic fields. We didn't say that the electric field is created by the magnetic field itself. We said that the electric field is created by moving magnetic field lines. Do I have moving magnetic field lines? Yes. If the magnetic field is changing, we do have moving magnetic field lines. But almost the moment that I create them, they will be moving at the speed of light. They will be going to infinity, so their density will always stay zero. There will be a moving magnetic field line which will be creating the electric field. Other questions? Well, let's see. Now, if you remember, let's look at the previous expression. In both cases, our definitions are the same. So this is one of them. And this is the other one. This is inside, and this is outside. Well, they have the same sign. So it just tells me that they are in the same direction. And if you see how they change as a function of the radius, this is E as a function of R. Let's say this is a large R. Now inside here, it increases linearly. It starts from 0 and increases linearly. And right when on the surface, they have the same value. When small r is equal to large R, this is large R, this is also large R. So just inside the solenoid or just outside the solenoid, they have the same value. So E is in fact a continuous function of R. So this is how E changes as a function of the distance from the center of the solenoid. Let's look at the toroid. Now, any questions on this one before we pass on? Why? Okay. Okay. So? You see, Gauss's law tells me that E dot ds is equal to 0 if Q enclosed is equal to 0. If I imagine any closed surface which doesn't contain any charge, then E dot ds is 0. But this doesn't mean that the electric field there is 0. in terms of electric field lines, this only tells me that if there is an electric field line that enters my surface, it should also leave my surface. They cannot terminate or they cannot start from a point inside my surface. And in fact, all these electric fields that are created by the changing magnetic field, they form closed loops. So if you imagine any closed surface, if they enter into this surface, they will also leave that surface. Meaning E dot ds for these new electric field lines will be 0 if we don't have any enclosed charge. Other questions? Well, this is our result. This goes linearly with R. This goes as 1 over R. No, this is the distance. As a function of time, this maximum point, it will be changing if the derivative of the current as a function of time will be changing, but it will have more or less this shape at any time, at any given time. Let's say at this point, at this level, we don't have any potentials. Okay, so let's see. Now here, we know that this, let's say the current is increasing, so this is the direction of the induced electric field. So if I put a positive charge over here, it will feel a force in this direction. So it will start accelerating in this direction. It will do an accelerated motion. Now let's see. Why couldn't we define the potential? Remember, when we were defining the potential energy, we said that if we want to define a potential energy, we take our object, we move it from point 1 to point 2, and we have to do some work as we go from point 1 to point 2. If this work is independent of the path, we just interpret it as we were storing energy in our system. We were doing the work that was causing the potential energy of the system to increase by the work that we had done. But in order to make this definition, the work that we are doing should be independent of how we go from point 1 to point 2. So only in that case we could define this potential energy. Now let's look at this case. Let's just assume that we take a positive charge from this point to this point, from point P1 to point P2. Now I can move this positive charge from P1 to P2, let's say along this semicircle. But in that case, I'm imagining a positive charge. I'm pushing against the force. So I will be pushing my object in this direction, and the object is moving, the charge is moving in the same direction, so I'm doing positive work as I go along this path. So does everybody agree? So if I take this positive charge from P1 to P2 along this path, I will be doing positive work. But if I take this object P1, this point charge, positive charge from point P1 to P2 along this path, then with 0 change in the velocity, in that case, the force is pushing it already along this path. I have to be exerting a force in the opposite direction, so I need to do a negative work. So if I take this point charge from here to here along this path, I will be doing a positive work. If I take this path, I will be doing a negative work. So I cannot really define the work, I cannot really talk about the work done as I go from P1 to P2. It depends on how I go from P1 to P2. It's just like friction. Friction depends on how we go from one point to the other one, the work done by friction. The same thing is for this electric field. Okay. Yes. Good question. Where does that kinetic energy come from? Did you get the question? So if we put some positive charge over here, it will feel a force, and hence it will accelerate. And we just said that it's a non-conservative force. So it will be moving. So as it is moving, its kinetic energy will be increasing. Where does that kinetic energy come from? Let me rephrase this question. It will be basically the same idea, but just a simpler version of the same question. Let us just imagine a positively charged ring. And I place this ring right on this circle. It is positively charged. Now, since it is positively charged, well, there is an electric field also in this direction. That ring will start rotating in the counterclockwise sense. Well, it has a mass, it will be gaining kinetic energy. Where does that kinetic energy come from? How? How does this ring change that work? You see, the source, you are saying it will be consuming some energy to change the current, but whether the ring is over here or not, it will be consuming some energy. It will be using some energy. You will study how much work it does, but it will be using some energy. Now we put this ring. Why does this ring change that energy? So, where does that electric field obtains its energy? Why? Due to what? But you say again, your answer should explain this fact. If I put a ring, if there's no ring, there are some changes going on. If I put a ring, what is changing? Well, there's a change in the flux whether I put the ring or not. So how does the ring modify my system so that I will not be having this violation of energy conservation? No, there are no eddy currents. So? Now, you see, this is the question. I have this solenoid, forget the ring, first of all. Then I connect it to a changing power source, so there will be a time-dependent current building up, and it will be, the current will be changing. We will see how much work, if any work, this alternating source does. And so here's our system. We have this alternating system. It will be creating this changing magnetic field, which creates the electric field. There's no problem with that. Now I say that, okay, let's build a machine that will create energy. I already have the electric field over here. Let me put a positively charged insulating ring over there, or a conducting, insulating ring, positively charged insulating ring. Well, why insulating? I want the ring to rotate, not just the currents created. So I put this ring over there. There's already the changing magnetic field, which creates this changing electric field, etc. When I put the ring will start accelerating because there's an electric field, which is gaining kinetic energy. Where does there's this additional kinetic energy in my system. Where does that energy come from? Of course, it's the electric field that is turning my system, but where does that energy come from? Okay. Yes, your friend has the answer now. You see, if the ring is rotating, there's a current over there. There's an additional current. This is the induced current. Now, Lenz's law already states that the induced current is always tries to eliminate the effect that creates it. Now, the induced current, okay, so my loop will be rotating like this, let's say. Kinetic energy is increasing, the current is increasing, but that means it is itself, that ring itself will be creating a magnetic field inside my solenoid, and hence as we said, there will be this back EMF. If we put a ring over there, and if we allow the ring to rotate, it will be harder to push current through our solenoid. So the battery or whatever the power source is, it will have to do some extra work in order to push the same current through our solenoid. That extra work will be converted into the kinetic energy of our ring. Energy is still conserved, if that is what you mean. Energy will always be conserved. Even if we cannot really, we cannot really define a potential energy in this case, energy will still be conserved. Since we are transferring energy to our ring, our battery or the power source has to be providing that additional power. The battery or the power source is giving this power to the ring. It will have to do some extra work due to the EMF created by this accelerating ring. So because our power supply, if this ring is accelerating, it's also creating an EMF in the solenoid. And hence it will be, the power supply should work also against this new EMF in the solenoid. Any last questions? Then see you on Thursday.